Swayam Prabha. Digital India. Educated India.
Character matrix, think of a square matrix, right. If you take the trace sum over I, aii, that is a trace, right, that is also called the character, and that is what we will use. Character is going to form the character of this course eventually, right. Now we move on to familiarizing ourselves with matrices, and that is all we will do. So, what is a matrix? An array of elements, that is fine, a collection of numbers, okay, collection of numbers, that is good enough. A two-dimensional collection of numbers, if you want to be more precise. Can you have three-dimensional collection of numbers? I can. I will take my son's blocks, right, and I will write 3, 5, 8, 9, 12, 13, 0, 1, 2. That is a matrix, square matrix, right. So, I will write it here, and then I will move 2 inches and I will start writing 3, 5, 9, 12, 15, 1, 13, 0, 3, and then again I will move 2 inches and I will write another array like that. Then I have a three-dimensional array of numbers. What is that called? See, she is very tense over there. So, this is called a tensor. Tensor, that is all a tensor is. A matrix is like a section of tensors. Matrix is a rank 2 tensor, right. So, do not be tense about tensors. Tensors are just arrangement of numbers. It is just that you cannot write it on a paper very easily, but you can take sections, fine. We'll come back to matrices. So, that is a matrix. Everybody knows what is a row matrix, what is a column matrix, right. Just one dimensional array of numbers, row matrix, column matrix, and they are also called vectors. They are called vectors, right. Now, we know how to add matrices, very simple, and subtraction is just a special case of addition, right. How many mathematical operations are there? 2. What are they? I will say 1. Multiplication is just addition many times over. So, there is only one mathematical operation, to be honest. Anyway, so multiplication of matrices is known. Can I take any two matrices that I want and multiply them together? No. What is the condition for multiplication of matrices? Number of rows should be equal to number of columns. And how do we multiply matrices? Row multiplied by column, that is enough. If you say that, I know you know what you are talking about, no issue, fine. Now, a special kind of matrices, and matrices that we like very much, are diagonal matrices. What is the meaning of diagonal matrices? Only the diagonal elements are non-zero, the rest is all 0. Why do we like diagonal matrices? And more fundamentally, diagonal matrices represent completely uncoupled systems. Only II is non-zero, right. That means what? There is no interaction between I and j. So, we have self sufficient set. That is why a very major problem whenever you use matrices is to diagonalize the matrix. So, when you study a little, or those who have studied already a little higher level quantum mechanics, you will see this diagonalization matrix is a very big issue. They want to do it all the time, because that is equivalent to what you have learned already. Does it ring a bell? What would this be related to? No. What I had in my mind was separation of variables. When you diagonalize, basically you have achieved separation of variables, right, because nothing is coupled with anything else, fine. diagonal and then you should not be scared if we write things in this notation. Aij, what is I, what is j? Row number, column number, fine. Aij is not equal to 0 if I equal to j and 0 if I not equal to j, fine, that is very easy. Next is real matrix, that also is extremely easy. Real matrix means a matrix of all real numbers, that is all. Aij equal to Aij star for all ij. What is Aij star? Complex conjugate. What is Aij into Aij star? Not necessarily 1, right, mod of Aij, right, mod of Aij, do not forget that it is not necessarily 1, right, mod of Aij square, right, mod of Aij square, good. Okay. Now, you know what is the meaning of transpose? Just interchange the rows and columns, right, interchange the rows of columns, and it is written in two ways. Sometimes it is written as A dash, easier to write, but then theoreticians like to complicate things always. So, it is also written as A with a tilde on top, I do not know what it is called, I will call it A tilde, that is called tilde, that sine wave kind of thing, that is called tilde, okay. So, I will call it A tilde, but it might maybe it is supposed to be read in another way, I do not know, to be honest, fine. So, in a symmetric matrix what will happen is that A is going to be equal to A tilde or A dash, right. What is the meaning of symmetric matrix? That if you interchange the rows and columns, nothing will change, you get the same matrix, okay. So, A equal to A tilde. So far so good, very easy, everybody knows everything. Now, let us slowly go up the complexity ladder by bringing in complex numbers, right. An adjoint or a Hermitian conjugate is defined as A tilde star. What does this mean? It is written as A dagger. So, what do you have to do? You start with a matrix, first transpose it, and then for every element that you get, write the complex conjugate, that is what it means. Understood? Sure? So, do not confuse transpose with adjoint, please. Adjoint is transpose plus complexifying the problem, right. Adjoint, or sometimes it is also called Hermitian conjugate. And this I showed already, but this entire part of matrices we are going to consult Bishop's book on that. There are many good books on matrix algebra, but then if you start reading from there, then this will not remain a course in symmetry, it will become a course in matrices, that will be a bit too much. Bishop's book is good enough. Now, adjoint or Hermitian conjugate, A dagger is A tilde star. So far so good, no confusion about what is an adjoint, Anju, okay. Now, since there is no confusion, let us work out an adjoint. A is given 1 4 I e to the power I 2 minus I 3 e to the power 2 I 1. I want you to work out A dagger. Let us finish this column 1 4 then minus I. Now, let us go to the top. What is the next element after 1? E to the power minus I, e to the power minus I, right. Then, oh, you are giving the bottom one, okay. Now, we are going left to right, okay, 3. Next, there is no issue with that. Next, okay, below 2, last one is unchanged, right. Which are the elements that remain unchanged? Diagonal ones, right. Diagonals will remain unchanged provided they are all real. If they are complex numbers, then you would have got their complex conjugates, but they do not change places, right. So, it is like, so what symmetry operation is it? What operation are, it is not a symmetry operation here, it would have been a symmetry operation if it was a symmetric matrix, but what is the operation that you are performing? It is rotation, right. It is like a square, it is a square matrix, right. So, it is like you take this diagonal, that is your axis, and you perform a rotation by what is the angle? 180 degrees, not 45. Okay. So, we know how to work out a dagger, right. Adjoint, it is the, what you do is you first transpose and then replace each element by its complex conjugate, fine. Next is Hermitian matrix. Have you heard the term Hermitian anywhere? So, tell me in what context you have heard this term? Hermitian operators. What are Hermitian operators? They give real eigenvalues, right. Everybody knows that, right. Hermitian operators give real eigenvalues. Who has said that? Other than the real Professor Datta, and is it really word of God written on a stone in letters of fire? No. Where does it come from? Let us see if we learn in this course, whether we can prove in this course that Hermitian matrices have real eigenvalue. So, this Hermitian, that Hermitian are not very different, right. So, Hermitian matrix. What is Hermitian matrix? A equal to A transpose. That means Aij equal to Aji star for all values of I and j. This is the definition of a Hermitian matrix. Have you learned Hermitian matrix earlier? Which course? Linear algebra, yeah, that is right. But now what we do in this course is that we develop a connection between linear algebra and quantum chemistry, okay. They are not divorced from each other. Is the definition correct? A equal to A transpose, Hermitian matrix. Oh, what am I saying? A dagger, sorry. Adjoint, A dagger. An example of that is this. Convince yourselves that this is correct. Work out A dagger. So, what do you have to do? You have to take these elements in the row to the column and then take complex conjugate. 1 remains 1, minus I goes here, and what is the complex conjugate of minus I? I. So, it becomes I. E to the power I goes to first row, first column, third row. What am I saying? First row, third column, and then e to the power I also becomes e to the power minus I. So, what was the first row is what we have got. Now, second row, take second row. I, where will this I go? To 2 1 position, and it will become minus I, complex conjugate. 2 does not change place, and it is a real number, no issue. 4 goes here, right. Then e to the power minus I should come to 3 1 and become e to the power plus I. 4 4, well this 4 earlier I got confused between these two 4s, anyway, and 3 remains in its whole place. So, this is an example of a Hermitian matrix, right, and this is not just idle gossip. These matrices actually become very useful for us in applications in chemistry, as we hope to see in near future, all right. But for now, let us not forget what Hermitian matrices are. What is a Hermitian matrix? A equal to A adjoint. Welcome to the club. Thanks for making the same mistake that I made. And last, not really last, second last, there is a, maybe this is last and there is a last after, one after last, right, one for the road. This is very important for us in this course, unitary matrices. So, we need to understand what unitary matrices are. What are unitary matrices? Unitary matrices are a little more complicated than Hermitian matrices. Here we have A dagger is equal to A inverse. The adjoint of a matrix is its inverse as well. When that is the situation, then we call it unitary matrix. A dagger equal to A inverse, or A into A dagger is equal to E. That is the definition of unitary matrix. So, one way of remembering it is when A gets unitary, right, unit. So, when A gets multiplied by A dagger, it gives you unit matrix. I do not know if that helps or not. A dagger equal to E, alright. These are very important for us, and we will learn a little bit about it before we close, but before that let us just for the sake of completion talk about another kind of matrices, that is called orthogonal matrix. Orthogonal matrix is a matrix where the transpose of a matrix is its inverse, A tilde equal to A inverse. So, do unitary matrices and orthogonal matrices have something to do with each other or not? Yeah. If A is a real matrix, then exactly. So, unitary matrix is the more general case, orthogonal matrix is a special case when we are talking about a real matrix, right. So, orthogonal matrices are really subsets of unitary matrices, okay. When all the numbers are real, then life becomes a little simpler, that is all. So, the point is orthogonal matrices are unitary matrices in when, but the only difference is that you do not have to worry about complex conjugate, you are working with real numbers throughout, okay. So, unitary matrix is the general case, orthogonal matrix is the special case, okay. And why are we so bothered about unitary matrices? Unitary matrices have this very special property that columns or rows for that matter of unitary matrices are related to a set of orthonormal vectors in general vector space. You can maybe not even think about in general vector space or part of it, just let us focus on the first part. Columns or rows of unitary matrices are related to a set of orthonormal vectors. Have you encountered a sets of orthonormal vectors anywhere? Did you not study there that the orbital, what is an orbital by the way? It is a one electron wave function. So, it is not a region of space where the finding the probability of the electron is maximum, that is the most popular wrong answer. It is an acceptable one electron wave function, okay. Now, do not those psi's behave like orthonormal vectors, right. So, orthonormal vectors are ubiquitous in quantum mechanics, you encountered them everywhere, alright, and that is the connection with unitary matrices. Columns or rows of unitary matrices are related to a set of orthonormal vectors. Of course, looking at this innocuous matrix, it is very difficult to believe what I am saying. Now, give me a break, you have an array of numbers and then you want to build this story that there is an orthonormal vector hiding there somewhere. So, it is only human to not believe what I am saying. But before you discount what I am saying, please do not forget I am not talking about a general case, I am talking only about unitary matrices, okay, and the proof of the pudding is in its eating. So, let us see if we can arrive at what we are saying. So, let us say this is a general matrix and let us say it is a unitary matrix, right. It is a square matrix in its most general form, right, n by n matrix. Can you write down the adjoint? What do we want to work with, transpose or adjoint or something else when we want to get unitary matrices? Adjoint or transpose? Sure? Then work out the adjoint. How will you work out the adjoint? Interchange rows and columns and then put star. Wherever there is no star, put a star, wherever there is star, remove star. Very easy. Done? What is A dagger? Is this right or is this wrong? Right, I got it right? Okay, great. Is this right? Huh? What was the row? A11, A12, etc., A1n. What is the column here? A11, A12, etc., A1n. So first row has become first column, and additionally I have put stars all over. My younger son would be happy to see this. He is past the stage where he gets stars in his classwork and homework, but still the fascination remains. Second row A21, A22, etc., A2n. Second column here A21, A22, etc., A2n with the stars, right? And then it is etc., y, etc. So let us go to the last row, an1, an2, dot, ann. Here you have an1 star, an2 star, dot, ann star. Okay. So you are convinced that this is a transpose? No. This is the adjoint? Right. Now, what is the property of unitary matrices? Property is written right here. A transpose is equal to E. What does that mean? If I take A and multiply with A dagger, then I should get unit matrix, right? What is the what does the unit matrix look like? In this case, n by n square matrix, diagonal elements are all 1, off diagonal elements are all 0, right? Right? So I'll just work out. We'll talk about the general notation later. Work out the 1 1 element in terms of these A's. What is the 1 1 element of A tau? A dagger. Yes, then plus. Achha, you are working out A dagger A. Why don't you do it A dagger so that we get the same answer? Your answer is also going to be correct, but it's just that it will, all the 1s and 2s will be interchanged. A11, A1 star plus A12, A12 star plus A13 star. Do you see the pattern? What is the pattern? This is what it is. A11, A1 star, 1 star plus A12, A12 star plus whatever plus A1I star plus again a lot of elements, then plus A1n star, and that has to be equal to 1, right? First element 1 1, there is 1. Do you see the pattern in the left hand side? Do you see the pattern? Every element is multiplied by its own complex conjugate, right? And you have added all of them, and what have you got? 1, right? Now, suppose I do not write 1, I write I. Okay, I is any integer between 1 and n. This will be perfectly valid, right? So, hold that thought. Now, let us work out something else. First row into second column, the 1 2 element, and even before you start working, what is that 1 2 element going to be? That is going to be 0, right? Unit matrix. First row multiplied by second column, what will it be? A11, A21 star plus A12, A22 star, and so on and so forth. Finally, A1n, A2n star, that is equal to 0, right? Ring a bell? Does that ring a bell? Does that remind you of something? Not only orthogonal, orthonormal. When you multiply one element with itself, or not itself, with the conjugate of itself, right, and then you add everything in the set, then you get 1, right. That means the normalization is 1, the sum of squares is normalized to 1, and when you multiply it by the complex conjugate of something else and then you add up, then you get 0, Is that not what we get in a set of orthonormal vectors, right? So, see, all of a sudden this innocuous matrix has taken up this magical property that you can associate it with sets of orthogonal vectors, okay. And now things get interesting. Now you can use it in quantum mechanics, now you can use it in symmetry. How do we write it in general? Sum over I A I j combine both and write, combine both. See, instead of 1 we had already put I, instead of the second digit let us put j. So, first one is what? Sum over I, so okay, sum over j A I j A I j star, sum over j from j equal to 1 to n A I j star, that is equal to 1, leave it there. Then next for the second one, right. So, now can we combine the two in one statement? Can we combine the two in one statement? In the first case it is equal to 1, in the second case it is equal to 0, right. So, either 1 or 0, what is that? Somebody gave that answer to, right, in some other context, it is Kronecker delta. Now, can I combine the two lines into one statement and equal to, I can write a Kronecker delta. Okay, you work it out. It is difficult to say if you, I have not written it intentionally, I want you to work it out, and this is what we will start with on Tuesday, alright. But the take home message today is that you see this, it is not just any matrix. When you work with unitary matrices, then you have this magical transformation into collection of sets of orthonormal vectors which are ubiquitous in quantum mechanics. That is why we can now use these matrices in quantum mechanics. So, next day we try to learn something more, we try to see, everybody knows about eigenvalue equation, right? Somebody said eigenvalue, what is eigenvalue equation? Eigenvalue equation, yeah, a operator operating on psi gives you some number multiplied by the same psi, that is called eigenvalue equation. The function is called eigenfunction, the number that you get is called eigenvalue. Now, next what we learn is that with using matrices you can write eigenvalue equation, the matrix eigenvalue equation, alright. So, that, and then from there we take we go on forward, and eventually we will be able to understand where this great orthogonality theorem comes from. That is the ultimate goal of this section of the course.